Okay, so we're going to be talking about what factors affect the rate constant K. So we're going to start pulling together now ideas of what's going on behind the scenes with these molecules and how is the rate of reaction explained by that. This is actually in your textbook section 12.6 and 12.7. I do not mean to confuse you. I'm going in a different order. It's just traditionally, this is introduced first before 12.5. So we will be swinging back around to that. One of the interesting things here is that we're going to start thinking of what's going on a molecular level to our molecules in a reaction, and how does that help explain the rate laws. So collision theory is a part of that. It's the idea that molecules have to collide to make products and react. And then it would follow that if there's more of them and they're more concentrated, that's going to lead to a greater reaction rate. So this next picture is just trying to get us to think about all these different molecules colliding and how that's going to affect the number of collisions. So in the first picture, you have two molecules of A colliding with two of B. And so you can have essentially theoretically 4 collisions. A goes with this B, A goes with that B. This A goes with the first B, this one goes with the second, and they can collide. So the total number of collisions that are possible is 2 times 2 there, which is 4. You add another molecule of A, then you could have 6 collisions. If you add another of B, you can have 9. So you can imagine that the number of collisions, if we were talking about Avogadro's number of molecules colliding with Avogadro's number of molecules, that it's a staggering amount as we start to think about all those different possibilities of molecules colliding. Okay, so this is a very important equation called Arrhenius Equation. It is given by this one here that's in this box. So this is our Arrhenius equation. And it is one that you should be able to not only understand conceptually, but also we're going to do some math with it. But let's start with the concepts. K is, again, our rate constant. A is what's called a frequency factor. That is the frequency at which these molecules are colliding. E of A is activation energy. We'll talk in a lot of depth on that. And then R is the universal gas law constant. And it's given as 8.314 joules per mole per Kelvin. If you recall from your gas laws chapter, there were 2 R's. There was the traditional 0.08206 that we use in PV equals nRT. But when we're talking about energy, that R has a different set of units and therefore a different numerical value. So in this case, 8.314, this would be given to you. I just want you to be aware that we use this particular R when we're concerned with energy, so that the equation has an energy dimension to it. And then our temperature for this equation will be in Kelvin. Okay, so as the temperature increases, more of those molecules are going to be colliding, and that's going to increase the rate of reaction. K will go up. But if you look closely at the relationship with E, right, it means that it's going to have an exponential relationship. So K increases as temperature increases, but that relationship is exponential. And we can see that in the next graph. So here is our rate constant K, and the rate constant K is plotted versus temperature in kelvins. And if you see here, the K goes up as the temperature goes up, but it's not linear, it's exponential. So here, the temperature is 288, and that's 0.0521. And then this temperature is 318, and that goes up to 0.332. So in other words, when things are exponential growth, they go up at a much more dramatic relationship, right? Not linear, but it dramatically changes with small changes in temperature. Okay, so there is an important concept called activation energy. I'll draw a little picture here. So let's say I have my reactants and products, and this is an energy diagram. So if we're picturing in this example, this will be an exothermic reaction. Delta H is negative. Energy is being released. Even when a process is exothermic, like the combustion of octane in a car, for example, there's still what's called an activation energy. And activation energy is this energy threshold that has to be overcome. Those molecules have to be at a greater energy than that threshold to start to make product. Up at the top, they'll reach what's called a transition state. And we'll look at that more closely in a few minutes. Okay, but the idea is this, is that as a reaction occurs, bonds have to start to break. So one of the examples that I like to give would be the combustion of octane in your car. Okay, so in the combustion of octane, octane is a very large hydrocarbon. I won't draw all the Lewis dots because that's going to be just crazy, but I'll show all the carbons there. I think that's 8 carbons. And you know the hydrogens are attached, so you did Lewis dots before. Okay, so for this process to start, those bonds have to start breaking. And that's really what we want to start thinking about, that activation energy, those molecules have to reach a certain energy threshold to where they can collide so bonds can start breaking and new bonds start forming. So on a molecular level, when bonds break, energy is needed. On this side, when bonds form, energy is released. Okay, and then overall, in the case of this combustion, more energy is released than you need. And that's where you end up with this negative enthalpy. But to get this process started, those molecules have to reach a certain energy threshold point. And we have to kind of push the reaction to happen. In the case of octane in your car, the spark plug helps to push this reaction towards product. Okay, but that does not mean it's endothermic, right? Because if you look, we put activation energy in, right? But then it comes back out and then gives us even more energy on this other side. Okay, now not all reactions have the same activation energy. Some reactions have a very high activation energy, some have a lower one. The smaller the activation energy, the larger K will be and the faster the reaction rate will be. I think it makes sense from a picture point of view that if I'm comparing these two pictures, if I have a reaction with a very high activation energy, that's going to be slower than one with a lower activation energy. So bottom line is all reactions have activation energies, but they're not all the same. Some processes they're more difficult to reach that energy point. Others have a very low activation energy. So it just depends on the chemical process that we're looking at. Okay, so this slide, I'm going to just click forward. I'm not such a big fan of it, so I'm going to click again. Okay, so now we're going to start looking at the idea of temperature. Okay, now temperature will never change activation energy. Okay, activation energy is what it is for a process. What temperature does is it creates more kinetic energy in the particles, leads to more frequent collisions, and so you have, at a higher temp, a higher fraction, or if you want to think of percentage, of collisions with enough energy to exceed E of A. Okay, so if you need a little bit more numbers, that's going to come on the next slide. Or actually, I actually think this is probably my favorite slide here. And then there's numbers on the next one. Okay, so this particular slide is a great example of how temperature and activation energy are linked. And I actually think conceptually this one is great. So here we have activation energy. Let's picture, now I know this doesn't have numbers on it as a graphic, but let's just say that the activation energy for this process is 100 kilojoules. Okay, here, fraction of collisions, this would be if you want to think of it like the percentage. A fraction is not quite a percent. If you take the fraction multiplied by 100, you get the percentage. But this would be the fraction or percentage, if you prefer, of molecules that are at a particular energy. Now let's start with the red graph. The red graph is showing us a higher temperature than the blue graph. So T2 is a hotter temp. So here's temperature 2. And what this is showing is what's called a Maxwell's distribution of energies. And so you have at this temperature a wide range of energies. Some molecules are low energy, some are high energy, and you have everything in between. Okay, now the area under this curve here, and it also extends all the way down through the blue, but I don't want to draw on that, is showing us that we have a pretty good fraction of molecules that are above the 100 kilojoules. Now let's compare that to the colder temperature, the blue one. The distribution of energies in the cooler sample, yes, the graph looks more dramatic and taller, but if you notice, it slopes down a little bit lower here. So if you're looking at the area under that curve, you have a much smaller fraction of molecules that's above 100 kilojoules. Okay, so let me restate this then. At a higher temperature, more molecules exceed activation energy. Okay, so at a higher temp, we have a higher number of molecules that exceed E of A. And that means then that if more of them are greater than activation energy, you're going to have a faster reaction. So you are not changing. You're not changing E of A. You're just changing the number of molecules that exceed that. So here, this is our activation energy. That did not change when the temperature went up or down. What's changing is how many molecules are at that energy At a higher temp, more of them are, so the reaction can go faster. Okay, so here's some numbers if you prefer. At 298, okay, here's some activation energies. Here's the 50 kilojoules per mole, 75, and 100. So notice as the activation energy increased, the number of molecules that can exceed it starts to go down. So the higher the activation energy, the less molecules exceed that E of A. So the reaction will be slower. Okay, now let's look at one of the activation energies, 50 kilojoules per mole. At 25 degrees, you have 1.70 times 10 to the negative 9. That's the fraction of molecules that exceed it. But look at 45 degrees, with the temperature goes up, that number gets bigger. So at a higher temp, we see an increase in the fraction of molecules exceeding E of A. So the reaction will be faster. Okay, Arrhenius equation has 3 different versions. And so the first version is the one that we just saw, that we just went through. And we started with this one. I like this one for conceptual. It kind of lays out everything that's affecting K. Temperature, activation energy. A is the frequency factor. That's how many molecules are in the correct orientation in space for collision. Okay, out of the 3 variables, it's the least discussed because normally we're concerned with activation energy. That gives us a lot of information of what's going on in a reaction, how fast or slow it's going to be. Okay, now there is a straight line form of the first Arrhenius. So here, if you recall from the previous slide, I showed you the graph of K versus temp, and I told you that it's exponential, so it's curved. But curves don't give us a lot of great info. Recall from Chem 200 that when we have a curved relationship, we can manipulate the data and generate a straight line form. The manipulation that's done is to convert K to ln K, and then the temperature is 1 over T. And what will happen is we end up with a straight line where it has a negative slope. Now I'm going to switch the straight line form to ln K equals negative E of A over R, 1 over T, plus ln of A. I like it a little bit better in this relationship. I think you can see it better as a straight line. Y equals mx plus b. If you notice, the slope equals negative E of A over R. So E of A equals negative mr. So this is an experimental way of finding activation energy. So let's stop for a second and think of all the graphing that we've done so far in our 3 weeks together, that we learned that you could find rate constant from the slopes of graphs, right? Depending on the order. Now what I'm introducing here is that we can find activation energy from the slope of this particular graph. So we can find E of A from the slope of the graph. And the graph has to be, though, ln K versus 1 over temperature, and that would be in kelvins. So that's the linear relationship. That's Arrhenius equation in linear form, ln K versus 1 over T in Kelvin. So that's Kelvin to the minus 1. And from that graph, you can solve for activation energy. Okay, now there's a third equation. Trying to get back to my pen. There's a third version of Arrhenius equation that is here. And I'm going to explain this one here in just a second. I'm going to click to the next slide, though. Okay, so this is showing a better graph than I just did, that we can find activation energy if we plot ln K versus 1 over temp. I do want to tell you, though, that I do prefer the Arrhenius equation in this format because it more clearly shows the y equals mx plus b form. So the slope equals negative E of A over R. Okay, so going back then, let's just say that we have some data for an equation, for a reaction. And if we're given the slope of this graph, we can always solve for activation energy. Okay, so let's just say, I'll give you a question. Let's just say that the slope of the graph is, let's say, negative 1475. Okay, and the units for this slope, y is unitless. X is Kelvin to the negative 1. So if you think of a slope, slope will be y's units over x's units. So the top one there is unitless, and then the bottom's Kelvin to the minus 1. So that flips the Kelvin up. So the slope of this graph will always have a unit of Kelvin. So if we want to then solve for activation energy, okay, then the slope equals negative E of A over R. So E of A equals negative slope times R. And can I write the slope as M, because that's kind of, it just looks weird to me this way. Okay, so go ahead and take a moment with your calculator to come up with the activation energy for those sample numbers. I'll erase this so I have room to, so you can pause me if you want. Okay, so negative 1475 Kelvin equals negative E of A over R, and the R is the 8.314 joules per mole per Kelvin. That's a given. So then we're going to take those two and multiply them together. We're going to get a pretty big number. So I'm going to get 1.2263 joules per mole. Notice that the E of A ends up being positive because those negatives canceled. Activation energy is always positive because it's that energy barrier. Okay, now in this example, the number's pretty big. And so most of the time, activation energies are given in kilojoules because just the numbers are more manageable. So this guy is 12.26 kilojoules per mole. And I dropped the 3 because the slope had 4 sig figs and the R has 4. Okay, so just like the last few sections, we're learning a lot about how we use graphs in kinetics. And so this is another graph, ln of the rate constant versus 1 over t in kelvins. This allows us to find activation energy. Okay. Now, in this case, here, the decomposition of hydrogen iodide. Okay, let me talk about this one. This one's going to be a little bit more intimidating. This says the decomposition of hydrogen iodide, there's your equation, has a rate constant. So we have K at 500 Kelvin and a rate constant of 1.10 times 10 to the negative 5 at 600 Kelvin. And it says we're going to find activation energy, or we want to. Okay, so this guy is a little bit different. We do not have a slope of a graph. So instead, what we're going to do is we're going to have a third version of Arrhenius equation, which is ln K2 over K1 equals negative E of A over R 1 over T2 minus 1 over T1. Now, where the heck did that equation come from? Our other Arrhenius equation was this. Right? That's the one we just practiced. Well, we could do some algebra, and I'll be honest with you, when I try to do the algebra part, I think it tends to be more confusing. So what I would just want to tell you is that if I have a temperature 1 and a rate constant at that temperature that I'll call K1, and then something changes like the temp, so then we would have a second equation. So let's say the temperature goes up, or you could just think of it more that it just changes. Then I can call these new conditions T2 and this new K, K2. Okay, now this might help you. Remember from Chem 200, we did like gas laws, like P1, V1 equals a constant, and P2, V2 equals a constant. And so what we did was we said, hey, let's go ahead and set those guys equal to each other, so that if I know 3 of these, I can always solve for 1 of them. The same thing's going to apply here, but the equations are just scarier. So the first equation, you have temperature 1, and you have a rate constant at that temperature. Then you have temperature 2 and a rate constant at that temperature. Okay, we can set these equal to each other. That would mean that we would set them equal to their ln of A. That's what they would have the same. And what would happen then when I do that is I will do some algebra, or I could do, after I set those equal to each other, and then we end up with this version of Arrhenius equation. Okay, I don't want to show you all that algebra because it just is a side detour and a distraction for this. So let's just look at our final version. The final version, what it does is it tells us that if I know, I'll check off for you. If I know, let's say, 4 of these variables, that I can always solve for the one I don't know. In this example, we want to find activation energy. So I will need the rate constant at 1 temp and the rate constant at another temp. And I'd have to plug in. So just like we would for P1V1 equals P2V2, if I said, I have a pressure and a volume, and now I'm going to raise the pressure, what's the new volume? That one's easy. This one's more challenging, but it's the same concept. We know 4 out of those 5 variables, and we can solve for them. So let's see what we have going here. We have temperature 1, 500 Kelvin, K1, rate constant 1, 9.51 times 10 to the negative 9. We have temperature 2, 600 Kelvin, and the rate constant at that new higher temp. And I think I wrote negative 19 and not negative 9. And we're going to solve for E of A. Okay, so let's go ahead and plug in. ln of 9.51 times 10 to the negative 9 over this number equals negative E of A. We don't know that. T2 Okay, so we have a lot going on here. And so let's talk a little bit about how we get to this point, is that when you're reading these, they're giving you temperatures and rate constants, and they're asking you to find E of A. So that's how you would know that you'd use Arrhenius equation. The next step is to plug this into your calculators and be able to do the algebra. So let's break this apart. Everybody has their x to the minus 1 keys on their calculator. So I would actually start with that. And I would grab my calculator and I'd say 600, 1 over x, or x to the minus 1, depends on your calculator, minus 500 x to the minus 1. Now, normally, I'm not a big fan of writing down numbers, but I think because we're not together, that in person where I can kind of walk around and show you stuff if you needed help, I think that I'm just going to write this down so that you can see if you're plugging it in correctly. Okay, we have that value. Okay, so always use your x to the negative 1 keys for that. Okay, now we have to solve for this guy, right? And these we can plug in. Now remember how you plug in your exponents. 9.51. You should all have your exponent key, -9. And then this would be 1.10 exponent key, -5. Okay, so let's look on the other side there. We're going to take ln and we're going to divide those two. 9.51 exponent key, -9 divided by 1.10 exponent key, -5. And I got -7.05. Okay, so you can pause me and go ahead and solve for E of A and make sure that you know how to algebraically now deal with all of these numbers. So you can pause me. I got 1.76 times 10 to the 5th joules per mole. Okay, so let's talk about how you should go about then getting this value. I'm going to erase that. Okay, you're going to have your ln's. You're going to do that division of the two k's, and then you're going to multiply by 8.314. That's going to come up there, and then you have to divide by your temperature subtractions. Okay, so essentially this would have been -7.05 times 8.314 divided by -3.33 times 10 to the -4. And let me just double check my numbers again. Yes, okay. And if we wanted to convert, sorry, I forgot the 5, 1.76 times 10 to the 5. And then if I wanted it to convert that to kilojoules, that might be cleaner. Right, just makes for an easier, we divide by 1,000 and we should get 176 kilojoules per mole. Okay, so if you need to pop into office hours to ask me to help you with your calculators and how to do these, then you should. And I think probably the cleanest way, if you didn't want to stop and get these numbers, which is not the greatest way, the cleanest way would have been to say, okay, I'm going to take ln, parentheses, divide the two k's, multiply by 8.314, and then divide by your inverse temperatures in the brackets. Okay. And there we have it. It was the same answer. If you wanted it a little bit prettier looking, then there you have it. Okay, this question I would have done if we had we have a holiday on Monday. So we won't be seeing each other then, but this is from your in-class questions. I believe it's number 6. And so this is the reaction of NaCl to 2NO plus Cl2. And that has an activation energy of 1.00 times 10 to the 2 kilojoules per mole and a rate constant of 0.286 at 500 Kelvin what is the rate constant at 490 Kelvin? So again, we're going to highlight this and figure out what variables we have and where we want to go, what we need. So in this case, we have E of A equals 1.00 times 10 to the 2. We have rate constant 1. At T1. Rate constant 2, we don't know, and we have a new temp, 490. When I say in class, these were the Zoom discussion questions, sorry. We were working on those, and this is one of those. Okay, so we're going to look at our Arrhenius equation, ln K2 over K1 equals negative E of A over R, 1 over T2 minus 1 over T1. So in this example, we're not solving for activation energy. We already have that, right? We're solving for the second rate constant, so that we have to isolate that term. Now, I think what's a lot better is if we go ahead and isolate it before we plug in all the numbers. So for this, you do have to remember something really important. ln of y equals x, and that's because e to the x equals y. So if I'm looking over at this guy, this is ln of y equals x. So e to the x equals y. So K2 over K1, our y, equals e to that whole big number, or big equation. Now, I know that you can do some subtractions there with the ln. Like I know you can do ln K2 minus ln K1, but ultimately, you're still going to have to do this part, which is the anti-ln. And then if I'm isolating again, K2, if I'm isolating this, then ultimately we do have one more step, which is K2 equals E to that big mess there, which I'll probably plug in numbers, times K1. Okay, so let's go ahead and plug those in. Now, if we look up at our activation energy, it's in kilojoules, but our R is in joules. So we need to make those the same. So to go from kilojoules to joules, I multiply by 1,000. So when I multiply this number by 1,000, I'm going to get negative 1.00 times 10 to the 5 joules per mole. And I won't have enough room, so I'm going to have to do a little bit of erasing here. So give myself some space. So then I'm going to divide by R. And then I'm going to multiply by 1 over T2, 490, minus 1 over T1, 500. And then remember, I did have to multiply by K1. And pause me and see if you can get the correct answer, because this requires us to do some really good calculator things, right? To really know how to work our calculators. So go ahead and give it a whirl. So at the end of the day, we should get 0.175. Whatever the units for K are, for the first K would be this. Same units for this one. So you really need to practice this. Please make sure you're using your x to the -1 keys in your calculators for those inverses, because if not, you're going to end up with too many parentheses. Okay, so that one's kind of a toughie for students. You have a homework on this that you should practice. I do think that it does get easier, but the hard part for students is to recognize when you use Arrhenius equation. And you'll use it when you are asked, what is the rate constant at some new temperature if you have a rate constant at another temp? Or what's the activation energy when you have rate constants at different temperatures? So be able to solve Arrhenius for K2, E of A, or T2, because that's how all the problems are going to ask you. It's either going to be solving for K2, rate constant 2, temperature, or E of A. Okay, our last bit is for A, which is the frequency factor. This is the idea that collisions between molecules, they have to have enough energy, but they also have to be in the molecules have to be in the correct orientation in space. So this is our A factor. And so this is just a graphic showing that some collisions will be ineffective, but if they have to be in the correct orientation in space to make product. And that there is what we would then think of as an effective collision. All right, I'm going to stop here because Arrhenius equation has a lot going on. And so then I would practice the assigned homework from this section, and that's going to be highlighted in the module, okay, for week 3.